Alright, scholars, we are going to take some quick notes on a very important concept here in physics. We're going to be looking at the area under a graph. Now, we mentioned it already a little bit in class and teased what this is going to be. I'm going to show you algebraically how we can get some useful information from the area under a graph. So go ahead and get your notes started here. We're looking at kinematics. This is Unit 2. And we are doing area under a graph. Alright, so we're going to first look at a constant velocity on a velocity time graph. So we'll just make a nice little sketch of a velocity that's in, of course, meters per second versus time graph. And that's measured in seconds. We'll just pick some object that's going at some initial speed, and it's going to stay at that speed v for some time. Let's say it goes for some time t. Okay, and so what we're going to do is we're going to look, I'll just shade that in there, we're going to look at the area under that graph. And you all know the area there of that rectangle is going to just be the length times width. So it's going to be just v times t. Now you might already see what that's going to end up being, but the easy way to do this is let's look at the unit analysis of that. So we tend to, when we do unit analysis, put that in the square brackets. So the units for velocity are meters per second, and the units for time are, of course, seconds. So lo and behold, when we take the area under the graph, we get meters per second times seconds. It ends up giving us just meters. And we know that is a measure of, then, displacement. So for an example, if we just plug some numbers in, let's say that v was 10 meters per second. We have, let's say it's a train going 10 meters per second. And we look at it for 100 seconds. That's t. So then the area would be, so this would be 10, and this would be 100. And so we would do 10 meters per second times 100 seconds, and we get 1,000 meters. That would be the, I'll just say the delta x. Okay, so important fact, I'm going to write it in red here. The area under a v versus t graph is displacement. This is an important fact that you need to know. You don't need to memorize it because you can always just go back and check the units that we're going to use. Okay? This is really useful graphically, and what we're going to find out is that we call this area, I'm going to write another important fact, I'm going to put it in red, the area under a graph. So by the way, let me pause there. When I say area under a graph, I mean between the line that represents the velocity and the x-axis. So like this is 0 in both the time and velocity. So when I say area under the graph, I mean the area between there and there, between the graph itself and the 0 on the x-axis. But anyway, so the area under a graph is called the integral. Okay, so that's a funny new word that you likely haven't seen before. Even if you're in calculus, unless you're really ahead, you probably haven't seen that word before. We're going to talk about how you actually compute the integral using calculus a little bit later. But for right now, this is a fact that we should know. Integral is the area under a curve, and specifically the integral for a velocity time graph is displacement. So we could restate this. The area under a velocity versus time graph is displacement. We could say the, scribble that out, the integral of v versus t is displacement. Alright. So I put a bunch of things that are important in red there. We're going to extend this to something that is moving. To be clear, this was a constant velocity. Now, this is true. I didn't say the area under a v versus t for constant. No. This is true in general. I want to show you why that's true. We'll do it with a constant acceleration now. So we'll put a line there. So now we'll try the same thing, but with constant acceleration. We'll draw ourselves a nice velocity versus time graph. And you'll be able to know that it's accelerating because we're going to see the speed change with time. So let's say our object starts at some initial velocity, we'll call that v naught, ends at some final velocity, v final, and all of that takes some time, let's call it t. So our object starts with some initial speed that's not 0, and it accelerates to a point up there. We can do the same trick where we look at the area under the graph. Now, we're lucky here because this is a nice geometric shape. We have two geometric shapes, in fact. So what we'll find in a moment is that we can look at the areas, and we're going to get something maybe a little bit surprising. Meanwhile, let's label this just a little. We got to do some algebra before we can actually show this here. So I'm going to shade in these two sort of distinct areas. We've got a triangle, which is an easy thing to find the area of, and then we'll do as well the this rectangle down here. So as you can see, we've got a rectangle with a triangle stacked on top. We have to do a little bit of work here to get to this, but it's going to be worth it for sure. So we have the final velocity minus the initial velocity here. What I mean is the length of this side of the triangle is just the difference between these velocities. And we're going to see if we can extract that from another equation, rearrange it to look like this. And we can pretty easily. So we're going to try to get that in this way. It might seem a little odd, but let me just show you. So if we take the acceleration definition, which is the change in velocity over the change in time, which is just final velocity minus initial velocity over time. Let's just count the initial time as 0. We can rearrange this. If I take and multiply both sides of this by t, we end up with AT equals V final minus V initial. So let's pause there. What we can do later when we get to the equations, wherever we see Vf minus V naught, we can just replace it with AT. So we'll pause there on that. And then what we want to do is look at the area. So the area under this graph is going to be that piece, which is t long. It's from here to here. And it's Vf minus V naught high. That's our red piece there. And the area of that's going to be easy to find since it's a nice triangle. And then, of course, we have our rectangle, which looks like this. It is V naught high and t long. So this is V naught, and this is t. Color that in. Okay. So let's turn that into algebra, just like we did right here. And we might get something surprising. You might be surprised here. So the area is, okay, so it's a triangle, 1/2 base times height. I'm going to write this in a specific way. I'm going to write it actually the height first, Vf minus V naught. So that's the height, and this is the time. So again, I'm just using, I'll scribble that in here, 1/2 height times the base. That's the area of the triangle. And then we, over here, need the area that's just length times width, so V naught times t. Okay, I'm going to do a couple of things at once here. First of all, we can substitute where we see Vf minus V naught. We can substitute AT into that, and then I'm going to switch the order of these just for clarity. So the area here is, again, I'm going to pull this up front, V naught t plus 1/2, and then instead of writing Vf minus V naught, remember we can write simply AT, and then that's multiplied by time. So lo and behold, look what we have there. Let me rearrange this one more time, and look what we get. We get V naught t plus 1/2 AT squared. That should look familiar. Hey, look, the area equals displacement here. Believe it or not, we just proved our kinematics equation. we just proved this one here. So that is delta x equals v naught t plus 1/2 at squared. So that's a pretty interesting result. And as we're going to see, finding the area under a graph can be incredibly helpful to us. The last thing I want to do is summarize what we know so far about the relationships between graphs. So here I just told you that if you have the velocity, you can get the displacement. Okay. What I want to do is summarize all of what we know so far about the relationships between graphs. And then you're going to use that on your homework. Okay. So we'll just call this roughly here graph relationships. How do they all tie into one another? So what we'll do is we'll put the main graph here. We'll say that its area under that graph goes over on this side, and the slope of the graph, we'll put that over on this side. So let's start, we'll just go down the line here. So if we start with position versus time, or x versus t, you all know that if you take the slope of that graph, we get the velocity. Right? That's the change in position over the change in time. That's velocity. Okay, that's easy. We've known that for quite a long time. I'll just tell you right now that this doesn't really have a physical meaning. The area under a position versus time graph. You can check the units and see that it would come out really odd. So don't worry about that. So this has no physical meaning. So we'll ignore that. Let's go down to the next one. The next would be velocity versus time. So that would be v versus t. And you all know that the slope of that graph is the change. So the change in velocity over change in time. That's just the definition of acceleration. And then as we've just now discovered, the area under a velocity versus time graph, that is the displacement. So this is kind of an amazing fact. I want to just pause here for a moment. So if you have let's just say a velocity versus time graph, and I'm just going to recreate the one we just had, you can get the slope equals the acceleration, and you can take the area, we'll do that in a different color, the area equals the change in x. So in a bunch of ways, or the displacement I should say. So in a bunch of ways, a velocity versus time graph is maybe one of our most useful types of graphs, because you can get basically any information you want about an object if you know its velocity. Which is pretty cool. Okay, moving forward. Let's finish up by talking about the acceleration versus time graphs. So that would be accel versus time, or just a versus t. Let's start with, we actually don't know this yet. Let me just show you what that would be in terms of the area. We'll do what we did a moment ago. We'll just assume a constant acceleration for right now. So if this is an acceleration versus time graph, and you do the area under that graph, just very roughly here, that would be, the area would be the rectangle here. So length times width, that would be a times t, which would be, let's see, so that would be meters per second squared times seconds. So if we cancel one of those, okay, so we get meters per second. So this is velocity. And more precisely, just so you all know, it's actually going to end up being the change in velocity for reasons we'll get to. So I'm going to just go back up to the top here. We had acceleration versus time. The area under that graph, that's the column we're under here, is the change in velocity, or delta v. I'm going to kind of box this information in. Okay. And then, kind of funny, most people love this here. So the slope of the acceleration versus time graph. Remember, we've always been talking about constant acceleration, so zero slope, there actually is a name for it. The change in acceleration or the change in time, maybe surprisingly, is called the jerk. So if you wanted to know how acceleration changes with time, you'd be measuring the jerk. That would be like the rate of change of acceleration. So in physics, or at least in high school and most of college, you don't normally deal with changing accelerations when you're talking about motion. This is more for like engineers and folks like that. Okay, so very quickly to sum that up, we have our position versus time graphs. If you get the slope, you get the velocity. We don't really ever take the area under that curve. Velocity versus time graph may be our most important graph because you can get the acceleration by looking at the slope, and you can get the displacement by looking at the area. Finally, a little messy down here, but if you have an acceleration versus time graph and you take the area under that, very importantly, by just checking the units, we showed that you get the change in velocity, and we learned a new fact, which is that the acceleration due to time, or change in acceleration with respect to time, is called the jerk. Thank you all so much for watching. Good luck.